So in this session, I want to take problems on sequence criteria. And then I wish to give some results which are useful to you while solving some typical problems as and when they come in the exam. And then we go with the concept of uniform continuity. So that is my objective with respect to today's session. Fine. So please take a note of it. After noting, you please tell. Right. So I think you have remembered the concept of what is meant by sequence criteria. Now let us take the problem that if the function f is defined as f of x equals to x when x is irrational and minus x if x is rational. So this is the function defined like this. Now the question here is, we have to prove f is continuous at x equal to 0 only. This is the claim of the problem, right? It is similar to the previous problem what we have considered. Since you are proving that f is continuous at the point 0 only means, if you take any other rational number or irrational number which is non-zero, so at every point f is discontinuous. In other words, you are saying that f is discontinuous on total R except 0. This is the actual meaning of the problem. Clear? That is actually we are going to prove. Any more queries? Is the objective clear? Right. Now let us take the first case that we will prove the continuity at the end. First I am going with the discontinuous part. So let us take that you take any non-zero rational number. Now I am going to prove f is discontinuous at this point. Construction of the sequence criteria is similar for every problem, no change at all. If you know how to frame the sequence criteria for one problem, that is applied for each and every problem. So the writing is similar, I am not changing at all. For each natural number, there exists an irrational, say an, between a minus 1 by n comma a plus 1 by n. As you know, in this neighborhood you can find so many rationals as well as irrationals. Since I have taken the rational number, I consider the equation as irrational. I am taking the opposite sequence. That is the underlined idea here. So this implies that an belongs to a minus 1 by n comma a plus 1 by n. So modulus of an minus a is less than 1 by n. that is the sequence an converges to A as n tends to infinity. Clear? Is that fine? Any questions, please? In the previous problem also you have written the same pattern, no change at all. So if you observe the sequence criteria, in the domain you have found a sequence which is converging to A, and you are verifying the image sequence converges to f of A or not. If this is happened, it is continuous, otherwise discontinuous. Is the picture clear or not visible? Is it visible what I have written here? Right? Then I will write here the part. So f is the function from R to R. I just adjust the camera. Right. So in the domain, I have found a sequence which is converging to A. Now I am verifying that the corresponding image sequence converge to f of A or not. This is my checking part. If this holds, means f is continuous at A. If it does not happen, means f is not continuous at A. Is this okay? The sequence criteria part? Yes or no? Now I am calculating f of an and f of A individually, and I am applying the limit. If you consider f of an, as you know, an is irrational sequence. As per definition of irrational, the element will be taken as it is. So f of an is nothing but an. If you calculate f of A, since A is a rational number, as per the definition, the value will be taken as minus of it, this thing. So f of A is nothing but minus A. If you calculate limit n tends to infinity f of an, it equals to limit n tends to infinity an is equal to A. So what happens? Limit f of an and f of A both are unequal. So f of an is not converging to f of A. Hence, by sequence criteria, f is discontinuous at A. That was the conclusion. Clear? Are you getting the idea? Yes or no? Yeah. First of all, you should understand what is meant by a sequence criteria. Everyone has a doubt it. Then only you will get the clarity over the procedure. The procedure has nothing to do in remembrance and applying. Only the concept has the importance here. Let me say, whenever you have a function defined between two sets, I am saying that the function f is continuous at a point A. If you want to prove that the function is continuous at the point A, the sequence criteria says that in the domain, you can consider all possible sequences which are converging to A. You take a sequence xn which is converging to A. You take a sequence yn which is converging to A. So it is possible to find so many sequences in the domain which are converging to A. You can write, because we have found one sequence here. And the statement is, whenever you have a convergence happened in the domain, since you have a function defined here between the two sets, for every element, corresponding image will be here. So for A, corresponding image will be f of A, and for every sequence, there corresponds a image sequence here, f of xn, f of yn, etc., etc. You know that xn converges to A. In the domain it is happening. If you checked that the image converges to the image, then we can say that the function is continuous at the point A. The idea here is, whatever the sequence you consider in the domain with the convergence, corresponding image sequence must converge to f of A. If you are able to find at least one sequence, say Bn is converging to A, and you verified that f of Bn is not converged to f of A, it means sequence converging, image is not converging. If you find at least one example, then immediately you can say that the function f is not continuous at A. That was the whole idea of sequence criterion. Clear? Yes or no? Please tell. Is the content clear? So here what happened, in this, in the beginning, I have taken a rational number A. I have to show the function f is discontinuous at A. That is my concept or task, whatever you call. So for this, if I apply the sequence criteria to prove that f is discontinuous at the point A, I should be able to find at least one sequence such that sequence is converging to A and image is not converging to f of A. I should find at least one example. So for this, what I have considered, I took the rational number A, I build an irrational sequence apart from rational sequence, because rational value always converges to rational value with an assumption. So I build a irrational sequence which is converging to A. So this part happened. Now I am verifying for the image convergence. So I have calculated image of an, image of A, and I have applied limit. So the limit is unequal, because f of an is not converging to f of A, because f of an value is A, f of A value is minus A. You cannot say that A converges to minus A. It is different. So f of an, if you calculate, its value is A, f of A value is minus A, both are unequal. So f of an is not converging to f of A. Hence, the image criteria is satisfied. In the domain, you have the convergence. In the codomain, convergence not happened. So, by sequence criteria, we can say that it is discontinuous. That was the whole idea. Clear? Any more queries for anyone with regard to this sequence criteria? Or you need more explanation on this? Any more queries from anybody? Fine. Then I am taking the second case. Case 2. So in the first case, what I proved, at the rational number A, f is discontinuous. In other words, at every non-zero rational number, f is discontinuous. That's what I proved. Now here I am proving that at every non-zero irrational number, f is discontinuous. That's what I am going to prove now. So you take A as non-zero irrational number. The same thing will come, no change at all. So for each n belongs to n, there exists an rational number, say an, between these two. So an belongs to these two values. So modulus of an minus a is less than 1 by n. So an converges to a as n tends to infinity. So now what happens? In the domain, I have found a sequence. Sequence is an which is converging to a. Now I am verifying for the image convergence. So you calculate f of an. You calculate f of a. You have assumed that a is irrational number, right? As per the definition of f of x, whenever you take irrational x, the image is the value itself. So f of a is nothing but a itself. If you calculate f of an, since an is rational number, for rational number, the function value is taken as minus of its value. So f of an is nothing but minus an. So if you apply limit n tends to infinity f of an, it is equal to minus limit n tends to infinity an. This is equal to minus a because an is converging to a. So limit an is nothing but a. Here you have minus, so it is minus a. So what happens? If you apply limit for the image sequence, its value is minus a and f of a value is a. Both are unequal. That's why I have said that a minus 1 by n and a plus 1 by n, in between you can have so many rational and irrational numbers. That's why I mentioned an is a rational one lying between these two. I am not particularly saying that a minus 1 by n is this. I am taking the value between these two. You should understand that. So if you have a doubt in that, you just draw the picture like this on the number line. Then you will have an idea. You just give me what is a number. Can you take a is equal to 3, say, or 4? Yes or no? What is the nth term in the sequence? An is the nth term in the sequence. I think everyone is getting confused with the thing that an belongs to a minus 1 by n comma a plus 1 by n. Here everyone is getting confused. I hope so. Am I correct? How it is actually happening? Right. For this, let us draw an example. then you will get a very simple clarity. Okay. Now, you fix that a is equal to 5 for our convenience. You are taking n belongs to the natural numbers n. So n starts from 1, 2, 3, 4, so on. Right. Suppose if you take n is equal to 1, a minus 1 by n, a plus 1 by n is nothing but 4 comma 6. Say. Right. So between 4 and 6, apart from a, you can find rational numbers as well as irrational numbers. Agreed? Yes or no? So if you calculate a minus 1 by n comma a plus 1 by n, whatever may be these values, but between these two you can find so many rationals and irrationals. So I will take an irrational number here, that I am calling it as a1 for n is equal to 1, right? So if you take n is equal to 2, then you are taking a2. So what will be the neighborhood you are taking? A minus 1 by n comma a plus 1 by n. So 5 minus 1 by 2 comma 5 plus 1 by 2. So we are taking 4.5 comma 5.5. So between these two, can you find an irrational number as well as rational number? Isn't it? Is it possible or not? Right. So that is nothing but second term a2. So if you take n is equal to 3, you can find the irrational one a3. So if you take n is equal to 3, what will be the neighborhood a minus 1 by n comma a plus 1 by n? Say. So a minus 1 by 3, a plus 1 by 3. So 5 minus 1 by 3, 5 plus 1 by 3 you are taking. So in this way, you are getting the values which are closer to 5. Yes or no? So in other words, you can imagine like this, that if you fix that 5, this is the first interval 4 and 6, then the next one 4.5, 5.5, so you are shrinking like this, and you are coming closer to 5, and at everywhere you are finding an irrational number. Here you will get an irrational number, here you will get, here you will get, here you will get. Yes or no? Now what happens, as and when n increases, you are coming very closer to 5, very small interval you choose. So you can say that an minus a is less than 1 by n. So as n tends to infinity, mod an minus a becomes 0. It means that an is almost equal to a. In other words, an is converging to a. That was the whole idea. If you say that in sequences Sn converges to L, it means that mod Sn minus L is less than epsilon for all n greater than or equal to m. In other words, from a term number m onwards, all the values are becoming equal to L. From a particular term number m onwards. Here also, as n increases, all the values an are becoming equal to a. In other words, you have found a sequence which is tending to a. That was the logic. Okay. Still you have doubts on it? Please tell. Is it still confusing to all? or is it applicable to all? Right. If anybody has any more doubts, you can ask. So initially, here you can say, this is the value A1, irrational number. This is the value A2, irrational number, A3, A4. Initially, all the values are distinct. So as and when you are moving, they are becoming equal to 5. Because if you write the sequence, all the values are different here. For a particular term number onwards, all the values are becoming equal to one single number. This number we are calling it as L. The same thing we are saying here. Okay? Right. So is the second part also clear for everyone? The case 2? Fine. Then I will go with the other part of the problem. So in the problem, it is asked that f is continuous at 0. So you have proved that f is discontinuous at every non-zero rational number. F is discontinuous at every non-zero irrational number. So all the rationals and irrationals are completed. Only 0 is remained with us. So at 0, we are going to prove that f is continuous. That is what you are going to do. So for this, I will use the definition technique. So you take epsilon greater than 0. We have to prove f is continuous at 0. So let x belongs to R such that mod x minus 0 is less than delta. So what is the property of continuity if you are checking? Very simple. If you are saying that f is continuous at 0, you are going to take a neighborhood for 0. So if you take any value here in this neighborhood, corresponding values f of 0 and f of x must be less than epsilon. The difference between these two. So you are going to build a connection between what is delta and what is epsilon. If you have chosen epsilon like this, then what could be the value of delta? You should just build a relation between delta and epsilon. So consider modulus of f of x minus f of 0. This is equal to, here two cases arise. If you consider f of 0 value, since 0 is a rational number, f is defined like this. For rationals, minus of the value. For irrationals, same value. Since 0 is rational, we treat, so this value is nothing but 0, even though minus 0 is nothing but 0. Minus, for f of x, in the neighborhood of 0, you can take any rational number and irrational number. That is your choice. You are just taking a value in the neighborhood of 0 such that distance between these two is less than delta. That is actually you are taking. So you can take x as rational and irrational. If you take x as irrational, f of x is nothing but x. If you take x as rational, f of x is nothing but minus x. Whatever the case may be, it is nothing but mod x. Accepted? Yes or no? Right. So if you calculate f of x minus f of 0, even though if you take x as rational or irrational, it is nothing but mod x. So you choose epsilon such that mod x is less than epsilon. So what happened here? Mod f of x minus f of 0 is equal to mod x, and which is less than epsilon you have chosen. And you are going to bring a relation between epsilon and delta. So this is the thing I have, and this is the thing I have. So comparing these two, if I choose delta is equal to epsilon, then f is continuous, because I am able to build a relation between delta and epsilon. In other words, if you take epsilon is equal to 1 by 2, delta is equal to 1 by 2. If you take epsilon is equal to 1, delta is equal to 1. If you take epsilon is equal to 0.6, delta is equal to 0.6. That's it. In other words, if you take epsilon is equal to 0.6 means you are taking all the values from minus 0.6 to plus 0.6. Any rational value or irrational value, whatever the value you consider. If we calculate f of x minus f of 0, it will be less than 0.6. That was the idea. In this problem, it is equal. See, the total thing is nothing but you should be able to build a relation between delta and epsilon. That's all. For many problems, delta and epsilon will be equal. For some problems, they are different. That also I have given an example, because in one problem, delta is equal to root epsilon. And while doing uniform continuity problems, delta and epsilon will vary differently. That will be best example for you while using this definition. The underlined idea here is, if you think that delta is a separate number, epsilon is a separate number, you won't get a full clarity. The actual idea here is, you are choosing a neighborhood here. This means you are choosing a delta neighborhood. In other words, no, if delta is equal to 0.2, epsilon is equal to, please understand, delta and epsilon are interconnected. Delta and epsilon are interconnected. You are choosing epsilon by means of delta and delta by means of epsilon. Actually, the thing here is, suppose you have taken a graph like this. This is my point A. I am saying that f is continuous at the point A. We know that continuous means the graph is continuous without having any breaks. Accepted? Right. So here delta means you are taking some values before A and some values after A. Delta is a small positive real number. Delta is greater than 0. So we say that A minus delta comma A plus delta is the neighborhood. In other words, in and around of A, you are taking the values in the domain and checking that corresponding function values are existed or not, and what is the gap between f of A and the function values. That is actually you are checking. And you are saying that if you take this much gap in and around of A, this is the corresponding gap between f of x and f of A. You are saying like that. In other words, values are existed, so that this is the variation in the graph. You are saying like that. Okay? That is the actual idea. Clear? In one way, you can say that f of x minus f of y by x minus y, if we calculate, we can call it as a slope. Okay. So slope is always less than or equal to a fixed number. In other words, you are saying like that. So the graph is varying with a fixed slope. You are saying like that. That was the underlined idea. As and when the graph is not varying with a fixed slope, you can understand that there is a gap. Then only the slope will be undefined. That was the interpretation we are going to take there. The actual idea between f of x minus f of a less than epsilon, modulus of. That was the thing. Okay? Right. Yes, while doing uniform continuity problems, we will do so many problems. Yes, if you are able to build a relation means you are saying that it is continuous. If you are unable to build a relation, then means it is not continuous. Actually, the value of delta depends upon two things. One, the point A, another one, epsilon. Because if you take the graph like this, here the curve is uniformly varying. It is, you can say, a sudden rise is there. So here delta value will be different. Here delta value will be different. Here delta value will be different. So you can say that this epsilon and delta in one way define the variation in the graph. So at some times you will have a large variation in the graph, so that delta and epsilon will very much vary. In sometimes very small variation is there, at that moment delta and epsilon will not vary, like that. Okay. So while doing uniform continuity problems, you can clearly understand there always delta and epsilon are different somewhat for majority of the problems. They are good examples for this differentiation criteria. Sorry. So let me take the other problem. It is also given in the previous year papers. F of x is defined by delta is equal to epsilon means is it continuous? Please understand. You are building a relation between delta and epsilon. If the relation is existed, then continuous. Relation does not exist means discontinuous. In a nutshell, you can feel like this. If you fix a point A, you take any neighborhood of A. Either you take the small one or you take the big one. Neighborhood is your choice. That is delta. You take a small neighborhood or big neighborhood, whatever may be. You should be able to specify that if this is my neighborhood, in this neighborhood, if I take any point x, I am going to calculate the corresponding function values f of x and f of a, and you are saying that this is the gap in the function values. The gap is not more than epsilon. That you are saying. That means the function values are almost coinciding. You are saying that. So means the graph is almost continuous without any breaks. If you say that it is greater than epsilon, so there is a huge gap between the function value and the image value. So the graph may not be continuous at that point. That was the idea. If it is less than epsilon, okay. If it is greater than epsilon, it is not continuous. So you are saying, if I have taken this much of neighborhood, this much of gap you can expect. If you have taken this much small neighborhood, this much gap you can expect. That is actually you are predicting in the graphs. Okay. Clear? So if you talk of a real life coincidence like this, right? Suppose this is a city. For this city, you have considered the neighboring villages. So you are considering a perimeter, 10 kilometers, 20 kilometers, 15 kilometers, that is your choice. So earlier, you know the effect of a cyclone or anything. So if you take a value x here, a particular village, this is f of a and this is f of x. So you are saying that the difference between this effect and this effect is almost less than epsilon. That means this much care you can take. If we say that it is greater than epsilon, the damage will be more. The effect is unpredictable. That you can say, if we talk of general terms. Okay? That is one way of interpretation into real life situations. Fine. Okay. So let us go with the problem. Delta and epsilon, for many problems they are becoming equal. For other problems they are different. One problem we have proved that delta is equal to root of epsilon. You can consider that. We have proved similar kind of problem earlier. And while doing problem with uniform continuity, always delta and epsilon are different. Delta is equal to epsilon will occur for some problems. For majority of the problems, delta and epsilon are different. Fine. Okay. So let me take the problem. So I have taken that f of x is equal to x if x is rational, 1 minus x if x is irrational. If you understand the previous problem, it is also the same type of problem, similar kind. Right. The task is prove that f is continuous at x is equal to 1 by 2 only. Okay. At x is equal to 1 by 2 only, f is continuous. So at every other point, f is discontinuous. That is we are going to prove. Here also the same construction will come, no change at all. So here you have two cases. Case 1, you take that a is not equal to 1 by 2, a rational number. I am going to prove that f is discontinuous at a. Case 2, a is not equal to 1 by 2, any irrational number. I have to prove that f is discontinuous at a. And finally, I should prove that f is continuous at x is equal to 1 by 2 using epsilon and delta technique. So in this way, I am going to solve the problem as it is of the previous case. Fine. So forming the sequence is exactly the same in the previous problem. No change at all. However, I will take case 1. So automatically you will get idea over the case 2. So in case 1, you take a as a rational number and a is not equal to 1 by 2. So for n belongs to n, a minus 1 by n comma a plus 1 by n contains an irrational number. Say an. So what you got? Mod an minus a is less than 1 by n. So an converges to a as n tends to infinity. Whatever the part you have written in the previous problem, same part we will write here in the construction of the convergence of sequence. No change at all. Now I am verifying for the image sequence convergence. So you consider f of an. I took that irrational sequence is an. When it is irrational, how the function is defined? 1 minus x. So f of an is nothing but 1 minus an. And what is f of a? Since a is a rational number, for rational number same value you should take. So f of a is nothing but a. So if you consider limit for this portion, so limit f of an is equal to limit of this part, so 1 minus a, because an is converging to a. So limit of f of an is 1 minus a, f of a is a, both are unequal. Therefore, sequence is converging to a, image sequence is not converging to the image. So f is discontinuous at a. Clear? So in getting the image sequence pattern, I am using the definition of f of x. What is f of a? I am calculating. What is f of an? I am calculating. And for f of an, I am applying the limit. Fine. So in the case 1, f is discontinuous at each rational number which is not equal to 1 by 2. In the same way, we prove case 2. Can I, or you can do it? Right. Is anyone required for the proof of it? For doing case 2? Right. You can do it. Or you want me to do? Can I or you? Right. And for x is equal to 1 by 2, we apply the epsilon delta technique. Here also, delta is equal to epsilon, you choose. The same thing will come here also, for this problem. Since you are getting boredom of this sequence criterion, I just want to give some of the results which are useful to you with regard to the continuous functions. If you have finished with this, and f is continuous at x is equal to 1 by 2, for that part I will write the proof on board. You just simply cross check. That is enough. So please check on this, what I have done. So if you consider f of x minus f of 1 by 2, you have two cases arise. X will be either rational or irrational. If you take x as rational, f of x is nothing but x. Since 1 by 2 is a rational number, f of 1 by 2 is nothing but 1 by 2. So the result is mod x minus 1 by 2. If you take that x is irrational, f of x is nothing but 1 minus x. 1 by 2 is rational, so f of 1 by 2 is 1 by 2. So if you simplify, that is 1 by 2 minus x. So whatever the case may be, if you simplify mod f of x minus f of 1 by 2, that value is nothing but mod x minus 1 by 2. So choose epsilon greater than 0 such that mod x minus 1 by 2 is less than epsilon. Since the two things are similar, if you take delta is equal to epsilon, then f becomes continuous. That's it. Is that part clear? Any more questions, please? So please take a note of it, then inform. I go to the results part. What are the useful results with regard to understanding the properties of continuous functions? However, they are useful for doing other parts of problems. After noting, you please inform. Thank you. So you have gone that continuous functions will have the satisfaction with regard to the algebraic properties. Now, one interesting thing is, if you take that f from closure a b to R is a continuous function, and not only that, f from S to R is a continuous function. So f is bounded and attains its bounds. So f is bounded means, since you know the function, after calculating all the values of f of x, f of x1, f of x2, f of x3, f of x4, for every point in the interval, you can say that this is the maximum value for f of x and this is the minimum value for f of x. In other words, in calculus we do that minimum and maximum of f, isn't it? Just like that. If the function is continuous, you can say f is a bounded function. In other words, you are going to say that modulus of f of x is less than or equal to k, where k is any real number. If you want a particular picture for it, this is the domain of f and this is the real number system. This is the interval I have taken, closure interval AB. So after calculating all the images here, you are saying that this is the smallest one, this is the biggest one. The smallest one we call it as infimum. The biggest one you are calling it as supremum. Usually we denote with the symbols small m and capital M. So small m is the real number, we call it as infimum of F, nothing but the smallest value of the images. Supremum, we call it as a real number which is biggest one among the images. Clear? And attains its bounds. It means that this real number will become an image of one value between A to B. There may be at least one value such that whose image is M. Similarly, there will be one value between A to B such that whose image will be capital M. That is the actual meaning of attains its bounds. Okay? If the function is constant, infimum and supremum both are equal. In that case, particularly for every value, it is nothing but infimum, it is nothing but supremum. So here, the statement is saying that for at least one value, you are attaining infimum, you are attaining supremum. If the function is constant, every value gives the same number, k. So that every number gives the infimum, every number gives the supremum. It is attained by everything. Fine. Right. However, this property is not applicable for open interval. Because if you define a function f from open interval 0, 1 to r by f of x is equal to 1 by x. Since x is not equal to 0, f value always exists, so it is a continuous function. Accepted? Yes or no? You know that 1 by x is a continuous function. Do you agree or not? Any queries for you? Yeah. So what I am saying, if f is a continuous function on the closed interval AB, then f is bounded and attains its bounds. Attains its bounds means this is the thing what I have specified. Is this picture clear? Right. I am saying that the function is continuous. It is not defined on the closed interval. It is defined on the open interval. Say open interval 0, 1. In that case, the function is bounded only, but there is no need to attain its bounds. Because for the function 1 by x, the smallest value infimum is 0, the biggest value supremum is 1. So what happens, as per the picture is concerned, you are taking all the values from 0 to 1, excluding 0, excluding 1, every value you are taking. The function is 1 by x here. You will get the images. You know that the image set is bounded. For the image set, infimum is 0, supremum is 1. But you cannot get 0 as image for any value between this. Similarly, you cannot get 1 as image for any value between 0 and 1. So, the function is continuous, accepted. The function is bounded, accepted, because this is infimum, this is supremum, but the function is not attaining the bounds. That means you cannot get the infimum as image of some number within this domain. You cannot get supremum as image of some value in this domain. Okay. Please understand that I took the interval, open interval 0, 1. Please understand. Open interval 0, 1. Near 0, so I am taking x by default greater than 0. So can it will be infinity? Tending to infinity is somewhat different. Particularly, I am taking x is greater than 0. In such case, okay, if that is the argument, then I will say f will not attain its infimum. Do you agree? Since denominator is how f of x 0 getting? Now let us do it. Excluding 0 and 1, I am taking every real number here. I am taking 1 by x here. In such case, if you take that 1 by it is tending to infinity because the value is almost equal to 0, but it cannot be 0 because you are excluding 0, right? That's why it is always greater than 0. You cannot get infinity. That's why I am saying that since you are taking the values bigger than 0 and less than 1, so the maximum value is not exceeding 1 and the minimum value will be 0 automatically. Do you agree with this argument? For this argument, will you agree? That's my whole idea to convey. Yes. X is equal to 1 by 2, the value is 2. So then, what will be the supremum in that case? What will be the supremum in that case? If 1 is not the supremum. So the image will be bounded between 0 and infinity. Right. So we are saying that am I correct now? 1 and infinity you are saying. So f cannot attain its supremum. Supremum cannot be defined. Because as long as you are taking the biggest value for x, then it will be different. Yes? Right. So in this case, we can just say that the function is unbounded because you are not able to specify both the bounds, what is infimum and what is supremum. Right. So if you want to give a valid argument, so apart from taking 1 by x, if you straight away take f of x is equal to x itself, then that may be true. 0 less than f of x is less than 1. Then we can say. Fine. So however, the thing here is, if you have a continuous function on the closed interval, it is bounded and attains its bounds. And if you take open interval, there is no need that it is going to attain its bounds. Sometimes the bounds are defined or not defined. undefined, you can take the example what we have seen now, right? So another interesting point is you know what is meant by root of an equation, right? So since you know what is meant by root of an equation, if you take a quadratic equation, cubic equation, anything generally, and you have encountered some of the problems in numerical methods, how to find roots of an equation using numerical methods. Can anyone have the idea with regard to that, the numerical methods? Right? So if you want to say that f of x has a root in the interval, usually you take the closed interval. What is the condition? Can you define? Anyone? Any one of you? Or you don't have the idea? Let me say, if we say that a point, say 5 is root of f of x. So what does it mean geometrically if you draw a graph? If I say that for the function f of x, 5 is root. So what does it mean geometrically? That's the x-axis. That's good. So it means that we just talk of real roots, not of complex roots. Let me say. So if we take that x square minus 5x plus 6, for this I can say that it is a quadratic equation. So obviously you will get a parabola. I think you are going to get the graph like this. 2 and 3. Accepted? Because it has two roots. It will cut x-axis at 2 points. 2 and 3. If you take the equation as x square minus 5x plus 6. So what does it mean? This is a continuous function and all these values are positive and all these values are negative. Accepted? Right. So from this, one useful theorem in real analysis is defined that we call it as intermediate value property, or also called as location of roots, given by the mathematician Bolzano. We call it as Bolzano's property or location of roots property. It states that, suppose if you say that this is the function f of x, this is the root you know. So if you take that this is the interval AB, now for the point A, f of x is positive, for the point B, f of x is negative, as per the graph is concerned. Accepted? Yes or no? Right. So here the statement comes. You take a continuous function f from closed AB to R, where f of A comma f of B have opposite signs. So one is positive and one is negative. Then you can find at least one value C, where C is lying between A and B, such that f of C is equal to 0. In other words, C is the root of the function f of x. That is called as Bolzano's property or intermediate value property, or you can call it as location of roots theorem. Is the statement clear? So you can find at least one value C which is lying between A and B such that f of C is equal to 0. In other words, if you take a big interval like this, so here you can find 2 points such that f of C is equal to 0. So the theorem gives the guarantee that at least one point you will get 0 if the function is continuous on the whole interval. Is that clear? Fine. In other words, from the graph itself, we can say that I am going to draw the graph. Forget about the root part. Suppose this is my graph. So if the function f from closely AB to R is continuous, then at the first point you can find a neighborhood such that f of A and f of x have same sign. Similarly, at the end point, you can find a neighborhood such that f of b, f of x have same sign. And similarly, if you take any intermediate point C in the neighborhood C minus delta, C plus delta, f of x, f of c have same sign. It is called neighborhood property. You please take a note of it. So here you are taking some values after A such that f of x and f of a have same sign. If f of a is positive, f of x is also positive. Similarly, you can find a neighborhood for the end point so that some points before B and B will have the same sign. If B is negative, f of x is also negative. Similarly, you can find a small neighborhood for C such that f of c and f of x will have same sign. That is called as neighborhood property. Okay? Is that clear? Please take a note of it. Then I am going to give one more property. So I want to draw the picture like this. This property is also given by Bolzano theorem. Suppose f is a continuous function from closely AB to R. Since f is a continuous function, every continuous function is bounded. So automatically, for all the images of f, you can find what is the smallest image, infimum, and what is the biggest image, supremum, which we can define automatically. So if f is a continuous function, the theorem states that between these two, the infimum and supremum, you take any real number. Okay. For this, corresponding pre-image will exist here. At least once. Or at least one value. That is, there exists some C which is lying between A and B such that f of C is equal to K. . Clear? And we are taking the opposite signs as well. Please take a note of that property. Actually here, we will say that in a simple manner, f of a is not equal to f of b. So you can even forget what is supremum and what is infimum. That also you can forget. You simply say like this. It is very easy to understand. So what is the statement of the theorem? If f from closed AB to R is a continuous function and f of a and f of b are different values, I am not talking about the signs itself. F of a and f of b are different values. Then between f of a and f of b, whatever the real number you take, say k, you can find at least one pre-image in the domain. Clear? That point I am saying it as C. If it is a constant function, it is not correct. For other functions, it is correct. Fine. Is the statement part clear? Any questions, please? Is the statement clear, what I said? Right. Then let us wind up our session here. Tomorrow we will meet with respect to uniform continuity. Or if you are interested, I will just give the definition of uniform continuity and we will do the problems tomorrow. As per your wish, I will continue. So if you want to give me the definition, I will give. Right. I will give the definition. Right. The main difference between continuity and uniform continuity is continuity is a local concept. So you are checking the continuity of a function point by point. F is continuous at the first point, second point, third point, and so on. Uniform continuity is a global concept. It means that you are checking the continuity over the domain. So actually what happens while bringing the relation between epsilon and delta, you are getting different delta values for a particular epsilon. Right. So the question here is, if I fix epsilon as one number, can I find one single delta over the domain satisfying the continuity criteria? So the thing is, if you want to write the definition of continuity function, we will write like this. For epsilon greater than 0, there exists delta greater than 0 such that mod x minus a less than delta implies mod f of x minus f of a less than epsilon. So here you are choosing delta around a. So delta is depending on the point also, not only on epsilon, on the point also you are choosing delta. So for uniform continuity, you define like this. This is the definition of uniform continuity. Now you can see the difference. So in the total domain, you can take any 2 points such that which have a distance of delta, then corresponding image difference is less than epsilon. The image value is less than epsilon. That is called uniform continuity definition. So here what happens? At every point you are choosing a neighborhood. So if you draw a real line, if I say that this is the point A, at A you choose a neighborhood. This is the point B, at B you choose a neighborhood. So if for every point, while defining continuity, you are choosing neighborhoods. So neighborhoods may be small, neighborhood may be big, depending upon delta. Here, apart from choosing different neighborhoods, you fix a single neighborhood. So you take any 2 points, x1, x2, whose gap is less than delta. Automatically, corresponding images gap is less than epsilon. If that is satisfied, you are saying that it is uniformly continuous. So in the total set, you can pick up any 2 points whose distance is less than delta, then corresponding images are less than epsilon, the difference between them. This is the concept of uniform continuity. Is the definition clear? Right. So tomorrow we are going to do the problems on it. Thanks for your good listening, and we will meet tomorrow. Then we will wind up our discussion on this chapter, and after Ganesh Chaturthi, we will start with the new concept, that is derivative. That will be more interesting to you. In that part, you will come across with the Rolle's mean value theorem, Lagrange's mean value theorem, Cauchy's mean value theorem one more time, which you have learned earlier in calculus. Tomorrow we have a class on uniform continuity.